In this video we're going to learn a entirely different method for solving differential equations called the LaPlace transform method. And before we start looking at how that is defined and developing the basic theory of it, let's talk a little bit about transforms in mathematics and their application to science and engineering. Transforms are used typically when we are trying to solve equations of a wide variety of types, and they are too complex to solve by straightforward methods. So if we mathematicians realize that if they transform the equation into another setting, another abstract setting, and then work with that new equation and then go back, take a reverse transform, it turns out to be an easier process, and sometimes or often a process that allows us to solve a wider range of equations and even to solve them more efficiently. So with transforms we get a new approach. We're able to sometimes solve things more efficiently, and the primary purpose would be that we're able to expand the range of types of equations that we can solve. So first let's define what a Laplace transform is. So we're going to take the Laplace transform of a function f of t designated as L, script L of f of t. And that is going to be defined as the integral of e to the minus st multiplied by our input function f of t, and then we integrate that from 0 to infinity dt. So to get a better feel for what a Laplace transform does to a function, we're going to take the Laplace transform of the basic types of functions that we encounter in solving a differential equation, starting with the Laplace transform of the function 1, the constant function 1. So the Laplace transform of the function 1 is 1 multiplied by e to the minus st, and then we integrate that from 0 to infinity dt. So when we integrate e to the minus st, we note that the integral of e to the minus st, or e to the minus, let's say e to the minus st is going to be e to the minus st divided by minus s. So we get e to the minus st divided by minus s, and then instead of evaluating that between 0 and infinity, since that is an improper integral, we're going to evaluate it between 0 and m, and then take the limit as m goes to infinity. So we're going to put that into its two terms, the term where we plugged m in and the term where we plugged 0 in, but we're going to rewrite e to the minus st, this part. We're going to rewrite e to the minus st as 1 over e to the st because it turns out to be easier to evaluate that way. So here we have that split into two terms, and then we're going to take the limit as m goes to infinity. So as m goes to infinity, since the denominator of that first term goes to infinity, that entire fraction goes to 0, and the second fraction we've got minus minus, which is plus, and we've got in the denominator s times e to the 0, so that's just the same as s, since e to the 0 is 1. So we wind up with just 1 over s. So the Laplace transform of 1 is 1 over s. So next we're going to take the Laplace transform of e to the minus at, so that would be e to the minus at multiplied by e to the minus st, integrate between 0 and infinity. So note that e to the minus at would be a type of function that we would typically encounter on the right-hand side of a differential equation. Excuse me, that should be e to the, not negative at, but e to the at that we're taking the transform of. So we set this up. We've added these exponents here together to get e to the minus s minus parentheses s minus at, because the a is positive and the s is negative, and so we're going to integrate that using the exponent rule to get this. First, note again that the integral of e to the at is e to the at over a, and so we're going to get e to the minus s minus a times t divided by the a, which is minus s minus a. We're going to evaluate that between 0 and infinity. We'll turn that into an improper integral on the next blackboard. Okay, so here we have this where we left off. This improper integral here, we have it set up on the next black. So we've plugged in the m and plugged in the 0, and now let's rewrite these terms, or at least this first term here, so that it does not have the negative exponents. It's easier to resolve, so we'll rewrite it like this. This numerator here is 1, and since it's positive, we put that in the first position here. And then for this other fraction, we've taken this negative exponent here and made it a positive exponent in the denominator here to make it easier to resolve. So then let's note that this factor in the denominator of the second term, as m goes to infinity, it goes to infinity, so the entire fraction goes to 0, and then this first term is all that remains, 1 over s minus a. So let's put these two transforms that we've obtained side by side, since they're actually paired up. They're actually very similar transforms. One is 1 over s, and e to the at is thought of as the shifting of the transform of 1, and so it becomes 1 over s minus a. We can generalize that in the next statement. So if L of f of t is capital F of s, then L of e to the at times that same f of t is going to be that same function capital F, but shifted to the right by a, so capital F of s minus a, which is what we got in this case, right? From 1 over s to 1 over s minus a. On this blackboard, we've written two new important Laplace transforms that of sine of bt and cosine of bt. They are obtained by integrating sine of bt times e to the minus st, or cosine of bt. So they're obtained by integrating sine of bt times e to the minus st, or cosine of bt times e to the minus st, and that's done integration by parts twice, exponentials times sine and cosine. So those integration steps are pretty lengthy. You'll find them in your book. I've just put the results here. And so let's add to these two results the two additional results we get when we shift both of these by multiplying sine by e to the at, or cosine by e to the at. So e to the at sine of bt, the transform of that, e to the at cosine bt, the transform of that, is going to give us these two new transforms here, here, and here. And so let's designate what the difference is between them and the ones above. So we've highlighted where s was in the original transforms. It's in one spot in the sine of bt, and in these two spots in the cosine of bt, and then the s s goes to s minus a in this case, and both these s's go to s minus a in this case. So we now have these four transforms, and let's collect together everything that we have in two columns, those that are not multiplied by e to the at and those that are. So we see these these two sets of transforms, these three, 1 cosine bt, sine bt, and then all those multiplied by e to the at over here. A large portion of the transforms that we need are contained on this chart. We'll need some others as we go along, but this is our building block for starting off with LaPlace transforms. So our next blackboard, we're going to find Laplace transforms of the differential equation itself, the y prime, and the y double prime. So the transform of y of t, when y of t appears in a differential equation, is easy. we just give that another name, call it y of s. Now the transform of L of y prime of t requires us to do a little bit of work using the integration by parts technique. So let's set that up. So we want L of y prime of t, which is going to be the integral from 0 to infinity of y prime of t times e to the minus st dt, integrated 0 to infinity. So we're going to solve this by the integration by parts technique, designating dv as y prime. We integrate dv and get b, which is y. We're going to designate u as e to the minus st, and du would then of course be minus s times e to the minus st dt. So the parts formula is uv minus the integral of v du. So let's set that up. So that's the u is e to the minus st. The v is y of t. We're evaluating that between 0 and infinity since it's uv is not in the integral anymore. And then v du, v is du is minus s e to the minus st, so we brought the minus s out front, and we put the e to the minus st inside, and that's multiplied by y of t, and then we're going to line this up a little better, put the uv there, and the integral of v du is the header on that integral. So let's designate or group what's inside that integral and make note of the fact that that's really just y of s in the brackets there, because y of s, because L of y of t would be the integral between 0 and infinity of e to the minus st y of t dt. And that's what we originally called y of s. So this expression right here in the yellow brackets is just y of s. So we can just rewrite designating what we had in our second term over here in the pink outline as y of s, and the minus minus as plus, we get this s, capital Y of s over here, and then we've just copied over where we left off here. So let's evaluate this first expression as an improper integral. So that's the limit as m goes to infinity of putting the negative exponent in the denominator, e to the s m minus 1 over e to the 0. And it's pretty easy to take those limits. This denominator goes to infinity. Now I had a mistake here. This should have been, I forgot the y of t here, which gives us a y of m here. And so, yes, the denominator goes to infinity, we do have to make sure that that function y is not too large, but all the functions that we will normally encounter in the function y won't cause a problem. So this part right here will go to 0, and then we're just left with 1. And also this numerator here, because we're plugging 0 into this expression, then the numerator here is going to be y of 0. So what we get out of this is minus y of 0 coming from this expression, and that gives us the s y of s, which was this term, and then minus y of 0 over e to 0, so minus y of 0. So here we have that designated. So let's box in this result and work on the y double prime using parts again. So u would be y double prime, or v would be y double prime, dv, sorry, and v would be y prime, u would be e to the minus st, and du would be minus s e to the minus st dt. So we put that together in the parts formula, we get this, and if we notice that this expression in the orange is just the transform of y prime multiplied by s, so that's just s that's just what we had back at this step right here, and so that turned out to be s, or s y of s minus y of 0. So if we use that information and take the s that we have out front and multiply it by what we had before, s y of s minus y of 0, then we get s squared y of s minus s. We get s squared y of s minus minus s times y of 0. And that is just for this part of our result. So we've got to deal with the other part, and so let's pick that up on the next blackboard. By the other part, I mean we've got to determine what this part right here is. So that's e to the minus st y prime of t between 0 and infinity, which is the limit as m goes to infinity of y prime of infinity over e to the s times m, and then minus y prime minus y prime of 0 over e to the 0. And so as m goes to infinity, this denominator here goes to infinity, and as long as y prime of infinity is not too large, as will be the case in the problems we encounter, this expression goes to 0, and this other expression is just minus y prime over 1, so it's equal to just minus y prime of 0. So putting all of that together, what we had was s squared y of s minus s times y of 0 from that last term, and now we're just going to subtract y prime of 0 from that, and so there is our transform of L of the second derivative. So let's put all of the information that we've learned together in one chart. So there we have all of the transforms that we need to take the Laplace transform of the left side of a second order differential equation. And when we combine that with our previous chart, which will give us transforms of right-hand sides of differential equations, we can solve differential equations using the Laplace transform method, which we do in the next two videos. The first one, we solve a non-homogeneous or a homogeneous differential equation with right-hand side 0, and then we show how effective the Laplace transform method is in solving a non-homogeneous differential equation, right-hand side not 0, without having to use the variation of parameters method or the undetermined coefficients method. So this concludes this video on the basics of the Laplace transform, how to take the Laplace transform on the left and right-hand side of a differential equation up to second order.